Hello everyone, March 22nd. Alright, let's do this. Palindrome linked list. Given a head, return true if it is a palindrome, or false otherwise. Can you do it in O1 time and O1 space? You basically reverse it. Oh, actually no. Reverse it probably is not gonna work. How would you do it? Maybe we can recursion it. We call a function for a node, which will return the last node. It's not really the last node, but how do you know when you reach the middle? That's the question. Reach the middle? You do know how you reach the middle. Okay, yeah, you can do it that way. You can find the middle point, okay, and then you reverse the rest, and then you try to compare, but you're changing. I'm trying to see if we can do it without modifying the original linked list. Yeah, that's one way. That's definitely one way you can do. You just find the middle and then just go with it. So in this case, we'll let it land on number 2, right? We'll let it land on number 2, and then I'll reverse the entire thing, right? And then it will be like 1 point into 2, and then we just compare them one by one. So yeah, that's one way to do it. But is that the best way to do it? Right? Is that the best way to do it? Can we? Oh. I think that's going to be my solution. I kind of don't want to think of anything else. I mean, that is ON, and then it satisfies everything. We'll write a function to reverse it. Right, we'll write a function to reverse it. And we'll get ahead. Yeah. Yeah, I mean, what else? Okay, that might work as well. Okay, so I'm gonna use a recursion and some very convoluted way to do this. It'll be interesting to see if it works. I am very interested to see how this will go. So we'll say compare. Okay, and we'll say list node. List node second. Okay. And then we'll run compare. List node current. We say if current. Oof. How do you know when it is the end? Well, I guess we'll. Yeah. Okay. Okay, that's fine. We can say if current or next. Ugh. What if it's hold on. We say even, all right, so we go 1 2. Let's go 1, and then we go 1 2. That's it. So yeah, we land here. And if we have another one, if we have odd number, we say 1 2 3 4 5. So fast goes here, slow goes here. Fast goes here, slow goes here. So we actually goes to the middle. Okay, we goes to the middle. And we don't want the middle. We want this one. Right, I want this one. Yeah, you know what? It's appealing, right? Very appealing. That yeah, so if it's even, fast go here, slow go here, and then fast done, right? Can go. So basically we slow ends here. Otherwise it's gonna be end. It's gonna be end here because fast go twice, slow go this, fast go this, slow go this, fast try to go, no go. So yeah, the other one ends here. This one will end here, and then we can say whenever we end, we always move to the next one. So this is our new start. So for this case, we move to the next one. So this is the new start, and I'll reverse it. Basically I'll set a dummy to point into this, okay, and I'll reverse the whole thing. I reverse the whole thing, and then we'll return. This is the start, right? So basically, we're gonna be, if it's 1 and 2, then we're gonna say 2 to 1, right? 2 will point to 1. And this will point into, nothing, right? This will point to none. And then what? And then we can compare from this to this. We'll compare them. Yeah, let's do it this way. I don't like recursion idea. I think it's stupid. So this is not. It's gonna be list node. Call it reverse, right? And then we're gonna call it head. All right, we did this yesterday, so we can just repeat it. So we have list node pre no, right? List node current is head. I say while head is not equal to no, list node temp head on next, head on next equal to pre, right? Pre equal to head, head equal to temp, right? So we keep moving until this, and then we're gonna return pre, because current will be nothing. Yeah, so return this. Okay, pre equal to head equal to temp, and then temp equal to this, head on next equal. Yeah, so that's that. And now we're gonna say list node slow head list node fast head, while fast is not equal to null, and fast on next is not equal to null. Okay, then fast equal to fast dot next dot next. And then slow. Okay. Once it gets out, then we say list node second head shall equal to slow dot next. Okay, and then we say list node reverse head shall equal to, we'll call reverse second head. And then what we're gonna do is while reverse head is not equal to null, if we'll say list node reverse head node equal to head. Okay, if head dot val is not equal to reverse head dot val, it's not head, it should be node, or return false. Otherwise, node equal to node on next, reverse head equals to reverse head on next. Now at the end we'll return true. Okay, so it satisfies, right? It satisfies, but definitely we made change to the original linked list. Let's see. Okay, we throw even, odd, whatever at it. Ooh, that was bad. Okay, that's not right. Everybody's true. Actually, I didn't try this one. So fast not equal to null, fast on next not equal to null, so fast equals to fast on next on next. So fast is null right now. Slow equal to slow dot next. Ooh. Actually, that we shouldn't move, right? Fast is not equal to null. Fast dot next is not equal to null. Then fast equal to this, and then slow need to move. Yeah, I feel like slow shouldn't keep going, right? Yep, I think that's the problem. And here, go here, right? Slow it here, and then fast is not equal to null. Fast on that, so fast actually go, and then slow go. So slow already at the right position. In this case, fast, slow, fast, slow, and then stop. So yeah, so this one stop at here. All right, this one stop at here. If I reverse this, this is gonna be this pointing to this pointing to this, and this will be pointing to null, right? But this still points to this. So if I check, and then we're actually checking the same thing. I think it's fine. I think it's fine. This just becomes slow. Right? I think it's fine. Yep. That's good, I guess. I guess it's good. reverse the second half. It is O(n) time and O1 space, but at the cost of modifying the input linked list. All right, let's take a look at whatever we did previously. What did we do this time? Okay, how about this one? Oh yeah, I think it's the same thing. Slow, fast. Yeah, slow, fast. Without restoring. Oh, I even tried to restore it. Oh, yeah, that's all right. Okay, that was good. All right, we'll move on. Sorting three groups. You're given a zero-indexed integer array, nums of length n. The numbers from 0 to n-1 are divided into three groups numbered from 1 to 3. Where number I belongs to group nums I. Hold on, the numbers from 0 to n-1 are divided into, okay, I got it. Notice that some group might be empty. You're allowed to perform this operation any number of times. Pick number x and change its group. More formally, change nums x to any number from 1 to 3. A new array res is constructed using the following procedure. Sort the numbers in each group independently. Append the elements of groups 1 to 3 to res in this order. Any nums is called a beautiful array if the constructed array res is sorted in non-decreasing order. Return the minimal number of operations to make nums a beautiful array. So okay, so we have these, and then you're allowed to perform operation, pick a number and then change its group. So I can change its group, basically change the value to 1 to 3 anything. And then after I do that, we'll get the numbers out, basically gets the index out, sort the index, and then lay them out. And then we want it to be beautiful, which means it's non-decreasing. So for the first one, we can actually check. Right, so the one belong to group 2, right, is 0. Group 1 is 1, 3. Actually, this is a stupid way of doing this. We shall say 1, 2, 3, okay? So we start with 0, and then that's 1, that's 2, 3 is here, and then 4 is here, okay? So if we lay them out right now, it's going to be 1, 4, 0, 3, 2, right? So basically what we want to do is the minimum number of operations to make this, because you just swap them, right? You can, that's not necessarily swap, because I can just, hold on, so like here is this, this, and this, right? So I need to make a non-decreasing. Non-decreasing. I mean, the numbers are unique, so they're always going to be increasing, right? So basically, okay, so this is out of, so I need to put this in the last one, right? So I need to change this into a 3. The false position to change into a 3. So when I do that, this automatically goes here. So that's one step, right? And then I need to change 0 Okay, 0 need to change here. Right, 0 need to change here. That's 2 steps. And I need to change 2. That's 3 steps. So basically, we have these groups of numbers, and you just need to know whether this number is belonging to the right group, right? And how do you know it belongs to the right group? Well, let me do this one more time. Yeah, what we can do, we can say group 1 is 1, 4, group 2 is 0, 3, and group 3 is 2. Okay, so that's that. And then it's not sorted. So sorted should be 0, 1, 2, 3, 4. So So 0 should be in the first group, but it's not. So 0 needs to move to the first group. Okay? And 1 is in the first group. And 2 needs to be in the first group. 3 needs to be in the first group. 4 is already in the first group. So everybody goes to the first group. Because the sorting is... Like, why do you think 4 needs to move to the last group? So you look at the first group, right? What we know is 0 must be in the first group. So that operation is for sure you have to move 0 to the first group. And then you check for 1. Right? To see if 1 is in the first group. And 1 is in the first group, so that's good. Right? Then you check for 2. Then you check for the current values in the first group if they contain everything that's already sorted. Right? Yeah. So like at the end, when you've done everything, the first group either contains everything, like from smallest all the way to wherever it is, or it is empty. Let me try another example. I feel 1, 2, 3. So 1 we have 0, 3 is 1, 2 is 2, 3, 4, 5. Yeah. So that's how it looked like to begin with. Yes, I can move everything here, right? But a better way will be move 1 here, move 3 here. Huh. So what's the end if I make this move? So we start with 2, 1, 3, 2, 1, right? At the end, it's gonna be 1, 1, because 0, 1, 2, 3, they become 1. So everybody become 1. In this case, we have 1, 3, 2, 1, 3, 3. So what we want to do is sum 1 followed by sum 2 followed by sum 3. I think that is what we want to do, right? And then we want to see the minimum number of steps, changes, to get to that state, right? To get to that state. So this is a 1, we don't change, and this is a 3. So we have two options. We either change into a 1 or we change it into a 2, right? So yeah, we change it into a 1 or we change it into a 2. So I can change it into a 1. I can change into a 1. If I change into a 1, then the next one, we can also decide to change into a 1. Or we can stay. All right, we can remain. Yeah, every step has like two options, right? Every step has two options. Or maybe we can say a DP index and a pre-value. What's the pre-value is? Depending on the pre-value, I can decide mine. If pre-value is a 2, then I can only be 2 or 3. If pre-value is a 3, then I can only be 3. If pre-value is a 1, then I can be 1 or 2, but I cannot be 3. Is that so? I think it can be 1, 2, and 3. That doesn't really matter, right? It doesn't really matter. So what we want to find out is DP because when we start, it's basically as 1, right? So we call DP01, right? We want to know from this towards the end, what is the smallest change to make it work, right? To make it work. And to do so, I can do DP1, basically depending on what my value is, right? So I can either change my value into 1, right? And then we can do that. Then you have to, the minimum of this will have to 1 plus, right? In this case, if we change, or in this case, I don't have to change, or I can change into 2, right? Then be DP1, 2, and now I have to add. So it'll be like 3 times. Okay, you want to try this? Yeah, I'm actually not quite sure if it's even gonna work. 25, right? 26. Not sure. This one, not sure at all. So def dp index and the previous value, okay, and then we're gonna return an int, the minimum number of operations. Okay. Then what? If index is equal to len nums I think this is returning 0 because you're hitting the last one, so the number of changes you need is 0, right? And otherwise, we have the previous value and we have the current, right? And it depends on, then we say if previous value is equal to 1, right? Then, all right, we can have a res equal to number of operations. So the maximum is just, yeah, let's put this one here, n equal to len nums. Okay, let's put it here, and n. So that should be n plus 1. This is the maximum possible, right? So if previous is equal to 1, right? If the previous is equal to 1, then you have a chance to be 1, to be 2, to be 3, right? You have those 3 chances. Then you say res shall equal to, then 4 current in range, right? This, it can be 1, 2, or 3, right? Be 1, 2, or 3. Then you say res shall equal to the minimum of res and nums index, right, equal to current. Now, not equal to current, because not equal, we're gonna have to like we can int this thing. I'm pretty sure we can int this thing, right? And this is the step we have to do. Then plus dp index plus 1 and current value, right? So that's if previous is 1, and if previous is a 2, then oh yeah, then we should actually do this. This is the pre, right? So we don't do this, we don't do this, right? So, and based on what pre is, if it's 1, we do 1, 2, 3. If it's 2, we do 2, 3. If it's 3, we just do 3 by itself, right? We do 3 by itself, and with that, and then we'll return res. Okay, then we will return dp. We start with 0 and the previous is gonna be 1. Okay, let's give this a shot. Oh, there's another one. I didn't even see that. Ooh, that looks good. Maybe that is the answer. So dp index and the previous v represents the number of minimum operations to make nums index towards the end with the previous group chosen as prev, satisfy, and make this satisfy the requirement. Okay. The requirement is to turn nums into a non-decreasing arrangement of 1, 2, and 3, right? Thus, for each dp index prev, depending on what the prev is, we can pick different values for the current. If prev equal to 1, we can choose 1, 2, 3 for the current. If prev is equal to 2, we can only choose 2 or 3. If prev is equal to 3, we only have one choice. We only have 3 as the choice, right? for the result, for the answer, we return dp 0 and 1. So we can call this ON. So O3N, right? I think that's the answer. Oopsie doozy. All right, let's hope this one works. It does. It does work. Not the fastest. I'm pretty sure if we convert this into bottom up, maybe it'll be faster. You know what? That could be a good exercise tomorrow. Let's see. I try to convert this bottom up. Maybe we can find some way to simplify this whole thing, make it even faster. All right, that'll be it. That'll be it for today. I need to eat and go to bed. I'll see you guys tomorrow.